Bismillah ar-Rahman ar-Rahim, chapter 20, section 1. We have to identify parts of the electrochemical cell and their functions, and we'll write the electrode half reaction for the cathode and the anode. Because oxidation reduction reactions involve electron transfer, so the net release or the net absorption of the energy can occur in the form of electrical energy rather than heat, because electron transfer from one part to another. The part for the oxidation, electrons are lost, and the part for, or the half reaction that represents the reduction, okay, electrons are gained. So when electrons move, they create electric current, and they represent electric energy. The branch of the branch of chemistry that deals with electricity related applications of oxidation reduction reactions is called the electrochemistry. Okay, this is introduction for the section. For the electrochemical cells, oxidation reduction reaction involve a transfer of electrons. Okay, so electrons transfer from the part that suffers oxidation to the part that suffers reduction. If two substances are in contact with one another, a transfer of energy as heat accompanies the electron transfer. Of course, because they suffer the electrons suffer certain resistance, and this resistance is converted into heat. If the substance that is oxidized is separated from the substance that is reduced, the electron transfer is accompanied by a transfer of electrical energy instead of heat energy. So once we connect between the two parts, the part of the cell that has reduction and the part that has oxidation, electrons start to move immediately, okay, between the two. Now let's start with the main important parts. The previous, it was introduction. The electrochemical cell, as you see, is composed of a container, and this container has two metal electrodes, or two metal plates, the first one of zinc and the second one of copper. Each one is immersed in its solution. So the zinc electrode is immersed in a zinc sulfate electrolyte, zinc sulfate, Zn SO4 solution, of course AQ, okay, and here I have a zinc solid, okay. The other electrode we have copper, okay, and immersed in the copper sulfate solution CuSO4, okay, طبعا AQ. And we separate between them with porous barriers. So the porous barrier separates between the two half cells, the first half cell and the second half cell, and at the same time it enables the motion of of ions through this barrier. Okay, the part of the electrochemical cell through which electrons were released or lost, okay, is called anode. So what is the definition of the anode? The anode is the part of the cell through which oxidation takes place, and the element is oxidized. It means it loses electrons. Electrons are lost. Okay, the cathode is the part of the cell here. The cathode is the part of the cell through which reduction takes place, okay, and the electrons are gained. Gain of electrons, okay. When electrons are lost from the zinc changes into zinc ions, okay, that are found now in the solution separate from the electrode, okay, and the electrons, the two electrons that were lost from each zinc atom, they move through a conducting wire to the copper. Okay, so they are gained by what? They are gained by the positive copper ions in the solution. Okay, and when copper ions gain electrons, so they are reduced, and then the copper ions now start to accumulate over the positive electrode or the cathode here. So the cathode carries a positive charge, okay, and the anode carries here a negative charge. So scientifically, the definition of the anode is the electrode through which oxidation takes place, or the element or the electrode loses electrons, or the source of electrons. Okay, the cathode is the part of the cell through which reduction takes place, or gaining electron takes place. So what gains electrons here? Copper ions in the solution, they gain electrons from the current and they start to deposit on the copper plate. Okay, and then the negative sulfate ions here, they get attracted to the positive ions of zinc here. So as we said, we provide porous barrier in order for these ions to move freely. Zinc ions move toward the negative sulfate ions, and sulfate ions can move easily toward the positive zinc ions. And by this way, we are creating what? We are creating a cell that produces electrical energy. So I can define the electrochemical cell as a device that converts chemical energy using some chemicals into electric energy. Okay, using what? Using two half cells, oxidation half cell and reduction half cell, that are separated with a porous barrier. Okay, here we can see the motion of the ions in and out the porous barrier. Okay, here I have one zinc ion. It moves in the other half cell in order to combine with the, or get attracted to the negative sulfate ions. And here a negative sulfate ion get attracted to a positive zinc ion. So this one is get attracted to this one, and this one get attracted to here. And these are the normal water molecules in the aqueous solution. Okay, so the porous barrier here enables free motion of the ions through the electrochemical cell. The electrochemical cell, electrons can be transferred from one side to other side through an external connecting wire. As we said, as you provide this external connecting wire, so you are providing a complete closed path for these charges to move. The electric current move in closed loop path, or the circuit. The circuit is a closed loop path, or the closed path through which the charges move, so that this movement of electrons through the wire is balanced by the movement of ions. So if I draw the electrochemical cell here, okay, this is the zinc, this is the copper, and now I'm connecting them with a wire. Okay, so the transfer of the electrons up, okay, is this is the porous barrier, okay, is balanced by the transfer of ions in and out. So here electric charges and here ions. Okay, an electrode is what? An electrode is a conductor used to establish electrical contact between electrical contact with a non-metallic part in the circuit. Okay, and the non-metallic part is called electrolyte. So if I am talking about the first half cell, which is the zinc half cell, okay, I have here a zinc plate. So zinc is what? Zinc is the electrode, which is the conductor, and this conductor is in contact with a non-metallic part, which is the electrolyte, which is its solution, zinc sulfate, SO4AQ, aqueous solution. Okay, so this, the electrode and its electrolyte together, they make up a half cell. This half cell represents what? It represents the oxidation half cell, or the part that is considered the source of electrons, because zinc here is oxidized, it loses electrons, and the zinc ions separate into the solution and so on. Okay, طبعا representing the negative electrode, which is the anode. Applying the same for the other half cell. Okay, if I'm talking about the copper electrode, okay, so I have here the copper immersed in copper sulfate solution, okay, AQ. So when I connect them with a wire, and at the same time I have to provide a path to connect also between them, because here I draw it in a separate way. Okay, so electrons are gained by the copper, so reduction took place here, and I can represent this half cell as the reduction half cell, or the half cell through which reduction occurs, or gaining electrons occur. طبعا copper ions, as we said, gain electrons okay, from the current and start to deposit here, okay? And we consider the cathode. What is the cathode? The cathode is the part or the half cell through which reduction takes place, and of course it takes a positive charge. Okay, this is the final shape of our electrochemical cell. So electrons transfer from the zinc toward the copper, from the anode to the cathode, okay, in the external wire, and then from the cathode to the anode inside the electrolyte or through the electrolyte. So inside the wire, electrons move from zinc to copper. Within the cell itself, the electrochemical cell itself, or within the electrolyte, the electrons move from copper to zinc, from cathode to anode down, from anode to cathode up. Okay. So what is the half cell? As we said, it's a single electrode immersed in its solution. Okay, a solution of each ion, as we said, zinc and zinc sulfate. This is the first half cell. An electrode, the electrode where oxidation occurs is called anode, and this is the definition of the anode, as we said. The electrode where reduction occurs is the cathode, and this is the definition of the cathode, as we said. Okay, so the example for an electrode here, the negative electrode is zinc. Zinc loses 2 electrons here, so we consider this step oxidation. Okay, and the copper ions here in the solution, they gain the electrons in order to get the copper. Okay, in order to get the copper, and this step is reduction, and the reduction occurs always within the cathode, as we said. So we are repeating what we explained before. Both oxidation and reduction must occur in the electrochemical cell, of course, or the electrochemical reaction. The two half cells taken together make an electrochemical cell. So the electrochemical cell is composed of the two half cells. Okay, the half cell represents the oxidation and the other one represents the reduction. The complete cell, an electrochemical cell may be represented by the following notation. We have certain notation we have to follow in order to represent our electrochemical cell. Okay, so simply we write the anode first and then the cathode. So we started with the anode, writing the anode electrode, which was the zinc, okay, solid, and then slash or this line separates it from its solution. So the solution was zinc sulfate, ZnSO4 AQ. Okay, and then we put a double line like this to represent the porous barrier, and then we write the cathode solution, okay, copper ions, and then the change it as a result of reduction into copper solid. Okay, so we can also represent the zinc as zinc positive ions, and it's not important to write the whole sulfate. Okay, so we just write zinc positive 2, okay, AQ. So this part of this half cell represents the oxidation, this half cell represents the reduction, and the double line here represents the salt bridge or the porous barrier that we provide in the cell. Okay. So we're done with this part now. Okay, the electrochemical cell that consists of zinc copper reaction is called a Voltaic cell, and we will explain the meaning of the Voltaic cell later. Okay, starting the Voltaic cell, section 2. We will describe the operation of the Voltaic cell, including dry cell and the lead acid batteries. By the way, the dry cell and the lead acid batteries are cancelled. Identify the conditions that lead to the corrosion. Also, the corrosion is cancelled. Okay. We will not take it. Describe the relationship between voltage and the movement of electrons. We will cover this part, and we will calculate the cell voltage potential from the table of standard potentials. Okay. For the Voltaic cell, a Voltaic cell uses spontaneous oxidation reduction reaction, and focus with this because the oxidation reduction reaction in the Voltaic cell, they are spontaneous. They always work in a continuous way to convert the chemical energy into electric energy. This is the definition of the Voltaic cell. A Voltaic cell, also called the galvanic cell, and focus with this, please. So we have here more than one term representing the electrochemical cell. So the electrochemical cell is a device that converts chemical energy into electric. And the most important type of the electrochemical cell is the Voltaic cell. That's equally, or we can use another term to represent it, which is the galvanic cell. Okay, the most common application for the Voltaic cell is in the batteries, different types of batteries, according to the type of chemicals that we use in these batteries. Okay. In the Voltaic cell, electrons given up at the anode, so oxidation takes place. Okay, pass along the external connecting wire to the cathode. So the cathode is the part through which reduction takes place, as we said. Okay, the movement of electrons through the wire must be balanced by the movement of ions, as we said before in the electrochemical cell. We're done with this part. Dry cells are Voltaic cells. Yes, dry cells are Voltaic cells, but we'll not go through the details of the dry cell. The three most common types of dry cells, we have zinc carbon battery, alkaline battery, and mercury battery. And also these three types of dry cells, we will not go through their details. Okay. Now focusing with the Voltaic cell, focus with the title. Practice models for redox reaction in electrochemical cells, or the Voltaic cells, or the galvanic cells. So you see that we have to provide to have reactions, oxidation half reaction, reduction half reaction. That's why they are considered redox reactions. Okay, connecting it with chapter 19 as we covered before. Okay, so here is the zinc strip, or the zinc plate immersed in zinc sulfate solution, copper immersed in copper sulfate solution. Okay, and we connect them with an external wire. You can fix any device you want to operate it, and it will be operated, or it will work on, because electrons transfer from the zinc to the copper, from the anode to the cathode, inside or within the external wire. Zinc represents the negative electrode, and copper represents the positive electrode. Done? Okay. This is a figure for the galvanic cell. In the galvanic cell, we separate between the two electrodes with the porous barrier. Okay? But still, both of them represent the same idea, a Voltaic cell or an electrochemical cell. Okay, details of the reactions inside the cell, not with us. Okay, all of this is cancelled. We will not go through these details. Okay, I'm showing them for you, or to you, in order to make sure that these parts are cancelled, so we will not go through them. Okay, because some students didn't take the material exactly. Even the corrosion, we cancel the corrosion. Okay, And now we will start the electrical potential. So in your textbook, starting from the electrical potential, this part with our material, inshallah. In the Voltaic cell, the oxidizing agent at the cathode pulls the electrons through a wire away from the reducing agent. So I want you to focus with this. In the Voltaic cell, the oxidizing agent means the agent that suffers what? Reduction. That is reduced. Okay? At the cathode, which is the copper. Okay? So the copper ions here are the reducing are the oxidizing agent, which are which is the part that gains electrons. Okay, they pull the electrons. Of course, they pull electrons. It means the electrons are attracted to these positive copper ions through the wire. They move in the external wire. So again, I will draw it here. Okay, zinc, copper, wire. Okay. So the electrons transfer to the cathode, through which electrons are pulled toward the cathode, and here the anode. Okay, so we consider copper ions the oxidizing agents. Okay, through the wire away from the reducing agent. What is the reducing agent here? Which is the oxidizing material, or the oxidized one. Okay, which part is oxidized here? The zinc, because zinc loses electrons and change into positive zinc ions, so it is oxidized, and we consider it the reducing agent. Okay, so the pull or driving force, on the electrons is called the electric potential. The amount of force affecting or acting on electrons to pull them from the anode toward the cathode represent the electric potential. Okay, as you provide higher or more electric potential, so the charges or the electrons are able to move faster, giving you higher current. As you provide lower electric potential, so the charges do not have enough force or energy to move from the anode to the cathode, giving you lower current, and so on. So the electric potential or the voltage is expressed in units called volts, which is the potential energy per unit charge. It means how much energy is given to a unit charge to move. If the charge carries much energy, the charge will travel faster, giving you higher current. If the charge doesn't have enough energy, low energy means low voltage, so the charge will move slowly, giving you lower current. Current is the movement of electrons, the rate at which electrons move, passed in units of, it's calculated or expressed in units of amperes. So the ampere is the unit for measuring the current. And now we can get the relation between the current and the voltage. So both of them, they have a direct relation. As voltage increases, you are providing more energy for the charges to move, so the current will be higher, and so on. Okay? Now, the tendency of the half reaction of either copper or zinc to occur as a reduction half reaction is an electrochemical. In the electrochemical cells can be quantified as the reduction potential. So we have another term, important term here, which is the reduction potential, and it is the ability or the tendency for any half cell, okay, to undergo reduction, to have reduction. Okay, reduction occurs with high percentage, low percentage, how much amount. Okay, reduction can take place within this half cell, so it determines something called reduction potential. Okay. The difference in potential between an electrode and its solution is known as the electrode potential. So don't mix between the terms now. We covered the term in the previous slide, which was the electric potential. What is the electric potential? The electric potential is the force giving to the charge to move, or the driving force on the electrons. This is the electric potential. Now we have another two potential. We have reduction potential and electrode potential. Reduction potential is the ability of certain half cell, could be copper half cell or zinc half cell, to undergo a reduction half reaction. Reduction. That's why we called it reduction potential. But the difference in potential between zinc and zinc sulfate solution, copper and the copper sulfate solution, the difference between them, we call it electrode potential. Okay? This potential difference or voltage is proportional to the energy required to move certain electric charge, as we said. So they are directly proportional to each other, the voltage and the charge. More voltage, higher charge; less voltage, less charge and less current. The potential difference measured across a complete Voltaic cell is easily, so we can easily measure the potential difference. It equals the sum of the electrode potential for the two half reactions. So if I got the electrode potential for the zinc half reaction and the copper half reaction, the oxidation half reaction and the reduction half reaction, and then we combine them together, in this case I can easily calculate the potential difference for any Voltaic cell or electrochemical cell. An individual electrode potential cannot be measured directly. That's why it has to be calculated in a relation with another. The relative value for potential of a half reaction can be determined by connecting it to a standard half cell. So back to the previous point, we said that the individual electrode, like zinc electrode, for example, its potential cannot be measured directly. So how can we measure it? We connect it to a standard half cell, okay, and as a reference, and we got the sum. With this electrode potential and the standard potential that we have in order to calculate the individual electrode potential for certain electrode. Let's apply. Before we apply, we need to know what will be the standard potential, that electrode potential that we have to know. Its abbreviation is She. Okay, a standard hydrogen electrode, standard hydrogen electrode, or the She. So it consists of a platinum electrode dipped into 1 molar acid solution surrounded by hydrogen gas at 1 atm pressure and 25 degrees Celsius. So these are the standard conditions through which the hydrogen electrode must be or must be found. So again, platinum wire immersed in a solution of an acid surrounded by hydrogen gas under 1 atm pressure and 25 degrees Celsius, and we consider this the standard electrode that we will use in order to calculate the electrode potential for others. Okay, so generally the standard electrode potential for the hydrogen electrode is 0. Okay, as shown in this reaction. Okay, the hydrogen gas, its oxidation state is 0. After losing the electron, changes from 0 to +1 oxidation. Okay, so this is the cathodic, the anodic reaction, or the anode. So the anode, this reaction takes place within the anode. Okay, and the positive hydrogen ions, they gain the electrons again and return back to the hydrogen gas again with 0 oxidation number. So you see that it suffers decrease in oxidation number, and this is the reduction, or let's say it is the cathode. Okay, that's why they call it cathodic reaction. So when we get the sum between both of them, it will be, of course, 0. They will cancel out each other. And here we have comparing reduction potentials of various models. Okay, here for iron, we connect the iron to the hydrogen electrode, or the She. Okay. So the voltmeter here reads negative 0.41, and here aluminum negative 1.66, here for zinc, and here we have for silver, gold, and copper. Okay, so we got all of these values and we put them in a table, and we will use this table as you see, as a reference for us to calculate the total electric potential for any cell. So you simply search for the half cell that represent your reduction potential, okay, and you will get the value and put the sum. The E node represents the total electric potential for any electrochemical cell, okay. We simply subtract the electrode potential for the cathode minus the electrode potential for the anode, okay. If they have reaction given to you in an opposite way, let's say for example Fe into Fe positive 2, okay. This is the given. What if I give you the reduction half reaction Fe positive 2 into Fe? Okay, so in this case you will take the same value, but you will change the sign. Instead of positive 2.87, it will be negative 2.87. Okay, we have extra values here and here also, that we will use them as a reference in order to calculate our electrode potential. Okay, so here this is for our Voltaic cell, the oxidation half reaction. This is for zinc. So when zinc gains electrons, okay, so the electric potential or the electrode potential is positive 0.67 volt, okay, when it loses the 2 electrons, and when it gains the electrons, this is the value negative 0.76 volts. So as you see that when you change the reaction from the forward reaction to the reverse reaction, you have to change the sign as I told you, according to the given. Okay. Standard electrode potential can be used to predict if redox reaction will occur or not. A spontaneous reaction will have a positive value for the E node cell. So again, when you see your electrode potential has, the E node has a positive value, so in this case you have a spontaneous reaction. But if the E node has a negative value, so in this case the reaction is non-spontaneous. How do we calculate? As we said, we calculate the electrode potential for the cathode minus the electrode potential for the anode, okay? Because we are calculating the reduction potential for the whole cell. They have reaction that has more negative standard reduction potential. Okay. Let's read the sample problem here that we have. Write the overall cell reaction and calculate the cell potential for the Voltaic cell consisting of the following half cells: iron electrode in solution of iron nitrate, FeNO3 by 3, and silver electrode immersed in silver nitrate solution. Simply, in order to solve it, okay, we have to represent the electrode potential for each half reaction. Okay, we got the value from what? We got the value from the table, and you will find the table in your textbook page 664. Okay, you can get all the values. So we will search in our table now. Open the textbook with me for the reaction through which the iron changes, or the iron ions or the ferric ions Fe positive 3, they gain 3 electrons and they change into iron, solid iron. Okay, and the value here, if you open the textbook with me, it's on the upper part to the right in the table, negative 0.04 volts. So we got it here from the table. And then what happens to the silver? Okay, silver gain electrons. So here we have what? Here we have reduction, and here we have oxidation. So sorry, another reduction. Silver ions also gain electrons because we are calculating the reduction potential for both of them. Reduction potential, both of them reduction. Okay, so searching in the table for silver. Yes, it's here in the middle of the left column. It's a positive 0.80 80 volt. Now it's clear. We will combine both. We will subtract the cathode minus the anode in order to get the final. Okay. So the E for the cathode, which is a positive 0.80 minus negative 0.04 volts, and the answer will be positive 0.84 volt. And of course we can describe this reaction or this redox reaction as a spontaneous one. Okay. طبعا this sample problem you will find it answered in details on page 665. 665. Okay, now let's start section 3, the electrolytic cells. In the electrolytic cells, we will use it in order to have some applications like the electroplating for jewelries, okay, and also in producing the rechargeable cells. Okay. So we will describe the nature of the electrolytic cell. We will describe the process of electrolysis. Okay, now the part for the electrolysis is cancelled. We will take the part for the electroplating and the rechargeable cells. Okay, some oxidation reduction reactions do not occur spontaneously, but can be driven by electrical energy. And this is the difference between the electrochemical cell and the electrolytic cell. The electrochemical cell is a spontaneous one, but an electrolytic cell is the cell that needs force or energy in order to force the oxidation reduction reaction to occur. If an electrical energy is acquired to produce a redox reaction and bring about a chemical change in the electrochemical cell, so we call this cell electrolytic cell. So the electrolytic cell is the cell that requires electrical energy in order to have a redox reaction or oxidation reduction reaction. Okay, in this figure we have the difference between, or we explain the difference between the Voltaic cell and the electrolytic cell. The Voltaic cell, as we said, the chemical reactions between the cathode and the anode produce electrons that transfer from the zinc to the copper and then through the electrolyte again. Okay, and the electrode through which oxidation takes place is called anode, reduction takes place is called cathode. And it's a source of electrical energy. But in the opposite for the electrolytic cell, I will supply the cell or connect the cell to an electric source like a battery, okay, that will force electrons to move in certain direction. Okay, also I have zinc and copper. The copper here, the electrons are driven from the copper toward the zinc, and here is the zinc. Okay, so the electrons are gained by the zinc plate. You see the arrow of the current. Okay, the electrons are gained by the zinc plate. It means reduction took place here. That's why we call it the cathode. And electrons are lost from this side. That's why this side is called the anode, or oxidation takes place here. So you see that the positions of the cathode and the anode are reversed in comparison with the Voltaic cell. The Voltaic cell is a source of electricity, but the electrolytic cell uses electricity in order to achieve oxidation reduction reaction. Type. What are the applications of the electrolytic cell? In which way do we use it or apply it? Okay, mainly in the electroplating, and we will see now its application. But before, let's revise again how does it work. There are two important differences between the Voltaic cell and the electrolytic cell. Number one, the anode and the cathode of the electrolytic cell are connected to a battery or an electric source, direct current source. But the Voltaic cell, okay, serves for a source of electrical energy, as we said in the previous slide. The second difference, the electrolytic cells are those in which electrical energy from an external source cause a non-spontaneous redox reaction. So in the electrolytic cell, I have non-spontaneous redox reaction opposing the spontaneous redox reaction in case of the Voltaic cell. Okay, so now we covered the second difference between them. In an electrolytic cell, electrical energy is converted into chemical. Oh, it's opposing what? Opposing the action or the function of the Voltaic cell. In the Voltaic cell, electrical energy is converted into chemical, not the opposite. So take care. This is the third important difference. In electrolytic cell, electrical energy is converted into chemical. I use the electrical energy to force the oxidation reduction reaction to occur. But in a Voltaic cell, no, the chemical energy is converted into electric. It's an electric source. Okay, the electrolytic process, an electrolytic process in which a metal ion is reduced and a solid metal is deposited on a surface is called electroplating, and it will be the first application for the electrolytic cells. I will use ions of certain metal to deposit on another in order to cover it completely, and we call this process electroplating. Okay? So an electroplating cell contains, number one, a solution of salt of the plating metal. Like, for example, if I want to cover a spoon with the platinum, for example, so I have to provide a solution of platinum. Okay? An object that an object to be plated like our spoon, and we will consider it or connect it in our cell as the cathode. Cathode means reduction takes place. Reduction means gaining electrons. So the ions of the solution will gain the electrons and deposit on the spoon in order to plate the spoon or cover the spoon in an evenly distribution way, of course. A piece of plating metal used as the anode. So I will use my platinum to be the anode. So again, I have, for example, any kind of a spoon, a metal spoon, and I needed to cover it with platinum. So I have to provide a solution of platinum, and I have to provide the spoon itself and connected it in my electrolytic cell as the cathode. And I will connect the anode with the metal that I want to use it in plating, which will be the platinum, for example. Okay? And this is the shape of our electroplating cell. I will connect it to what? To an electric source, as you see. Okay? My spoon, for example, will be the cathode through which reduction takes place. Electrons are gained. Okay? And my metal that I will use as a source of these ions will be the anode, immersed in a solution of this ion. Okay? A solution of this anode. So here I use for example, the anode is silver, immersed in silver cyanide solution. Okay, so as we connect it to an electric source, a battery, so electrons are forced to move from the negative of the battery to the positive. So the negative is connected to the ring or the spoon that I want to cover it with the silver as the cathode. So the silver ions in the solution will gain these electrons and start to deposit on the spoon or on the ring in order to cover it. Okay, and then the electrons transfer to the silver plate and back to the battery again, and so on. Okay, so electrons are gained where? The electrons are gained here in the cathode in order to accumulate or allow the silver ions to deposit on the plate or the ring that I want to cover it with the silver. And the opposite, the cyanide ions, are attracted to the opposite direction. So we said that the motion of the electrons is balanced by the motion of ions and so on. Okay, this is the idea of the electroplating. Now, the second application is the rechargeable cell. The rechargeable cell combines between oxidation reduction chemistry of both Voltaic cell and electrolytic cell. An application for the rechargeable cell is the car battery. Okay, the car battery, it converts chemical energy into electric energy, and in this case we consider it a Voltaic cell, but it can be recharged. It means I can connect it to an electric source and reverse its reactions again in order to maintain the reactants again to continue working, and in this case we consider it electrolytic cell. When a rechargeable cell converts chemical energy into electric, it is Voltaic. When the rechargeable cell, it operates as the electrolytic cell, it converts electrical energy into chemical. In this case it serves as an electrolytic cell. Okay, an example, our car battery is here. We have lead oxide plates, okay, a solution is sulfuric acid, okay, lead plates, okay, and we have طبعا cell connectors between them. Let's see the oxidation reduction reactions and understand more. Okay, a standard 12-volt automobile battery is a set of 6 rechargeable cells. So you know that a battery is composed of many cells. How many? 6 rechargeable cells. Let's see the anode half reaction. The lead ions, the lead atoms, okay, they react with the sulfate ions in the solution, because we said we provide sulfuric acid solution, H2SO4AQ, okay. So they lose electrons. Here the oxidation state is 0, here the oxidation state is positive 2, okay, and combine with these two, with the sulfate ions here, and 2 electrons are released. Okay, so we consider this process, the release of electrons or the loss of electrons, oxidation, okay, which is the anode half reaction. The cathode half reaction represents the lead oxide as a solid with 4 hydrogen ions from the solution and sulfate ions from the solution, and the 2 gained electrons from the oxidation step. Together they form lead sulfate again, and liquid water is produced. Okay, so when electrons are gained by all of this, so we represent this step, the reduction half reaction. The reduction half reaction that represents gaining electrons, and it occurs within the cathode half reaction or the cathode half cell. Now, the net oxidation reduction reaction or the redox reaction, we will combine between both, back to the previous slide, Okay, when we combine with between the oxidation and reduction half reactions, we will cancel the 2 electrons together, and then we will write all of our reactants together and all of our products together in order to get the final net redox reaction. So lead solid with solid lead oxide with solution of sulfuric acid, they produce together in a redox reaction lead sulfate and water, liquid water. Okay, once the car is running, the half reactions are reversed, they move in the opposite direction by a voltage produced by alternator. So I have an alternator or a part fixed within the battery that allows during running or during turning on our engine, okay, that the battery can use the reverse reaction in order to retain our reactants again. The reactants are the lead oxide, and the sulfuric solution. Okay, acidic solution are regenerated again, okay, to maintain them again. A battery can be recharged as long as all reactants necessary for the electrolytic reaction are present and all reactions are reversible. So once I provide chemicals that are able to achieve reverse reaction, so in this case my battery fits with the use as rechargeable cell or rechargeable battery. Okay, the part for electrolysis not with us, and the end of section 3 will be the rechargeable cells, and by this way, which is this slide, and by this way we're done completely with chapter 20. So you have to identify the type of cell, you have to identify the cathode, the anode, which electrode has oxidation process or reduction process. Also you have to identify to determine how to get the electrode potential from the given table, to calculate the total electrode the anode for the cell, as we said, the cathode minus the anode, the electric potential for the cathode minus the anode, and we have many applications for these calculations in the textbook. All of their answers will be with you in order to use it as a reference. Thank you and good luck.